I'll start. Heavenly Father, we thank you for this day. And Lord, I thank you for these students. Just ask you to bless this time today, Lord. In your name I pray. Amen. I think the only thing that I did not provide a solution for in the math battle was what? The very last problem, right? That's a problem that I made up for you guys that was not on my test, actually. My test had some other problem, which I deleted. But you saw in the solution if you looked at it, right? The solution to Math Battle 2, there's a problem in there that wasn't on your Math Battle. I deleted that one because the focus of our class has been a little bit different. So problem 15, I should talk about with you guys. Let's see here. We're supposed to find a parameterization and calculate the desired object. So let's see here, A. We've got x squared plus y squared minus 4z squared equals to 1. All right. We're supposed to find parameterization of the tangent plane at 2, 1, 1. Now, before I solve the stated question, what if instead of saying parameterization of the tangent plane, what if instead we had read the words find the equation of the tangent plane at 2, 1, 1? What would you have done then? I would hope we would have been like, aha! That's easy picking, right? Call this thing f. So we just say, yeah, gradient of f is, what is it? Excuse me, 2x, 2y, minus 8z, right? Therefore, nabla f at the point 2, 1, 1 is what? It's 4, 2 minus 8. And so tangent plane, 4 times x minus 2 plus 2 times y minus 1 minus 8 times z minus 1 equals to 0. Game over, end of story. That would be the equation of the tangent plane. We calculate the gradient of the level surface, and we use that to construct the normal, and then we write down our plane with that normal and the given point. But that was not the question, right? What was the question? Yeah, find a parameterization of the tangent plane. So that's annoying. So the way I wanted to do that here was to come up with a parameterization of the surface, right? So, excuse me, I would look at this as x squared plus y squared. Well, let's see here. If I could think of this as being like cosh squared, if I could make this into a cosh squared, say beta, and if I could make this into a sinh squared beta, then that would be productive. So this to me suggests then x is equal to cosine of theta cosh beta, y is equal to sine theta cosh beta, and z, well, I got that fourth there, which is kind of a drag. So to get rid of that, I need to divide by 2, 1/2 sinh beta. And I think, so I did a little bit of guessing here. When you do guessing, what you got to do? You should check your answer. So allegedly, this squared is my x squared. Sine theta cosh beta squared, right? And then minus 4 sinh beta over 2 squared, right? What's that equal to? If I did my job, that better work out to 1. Right? If it doesn't work out to 1, it's not a parameterization of this thing, is it? So the first two things become cosine squared theta plus sine squared theta times cosh squared beta. And then we get minus sinh squared beta from that. This, of course, becomes 1. So we get cosh squared beta minus sinh squared beta, otherwise known as 1. Woohoo! Okay. Like, well, how am I supposed to know that? Well, there's a simple answer to that. I wrote notes that I gave to you guys. I've got like 4 or 5 pages where I discuss how to parameterize everything from cylinders to hyperboloids to paraboloids to ellipsoids to all your oids, right? All your different oids. So if you go back and look there, you'll see I have lots of examples of how to parameterize surfaces, right? So if I were you, I would write down a few on my card so I have some sense of what I'm doing, right? Could you parameterize a sphere? Some say yes, yeah. Now, I mean, this isn't the biggest thing on the test, but it is a thing, right? I ruled this out for test 1, right? I'm not ruling it out for test 2. Now, I still am not going to ask you, name that surface, right? Is this a paraboloid? Is this a hyperboloid of 1 or 2 sheets, right? I'm not adding that to your list of responsibilities for this test, but I would like you to be able to parameterize things like this, right? Okay. So if you didn't understand that, I mean, it would be good to go back and I think that may technically be on the chapter that's before the chapters which is focused on in this test, right? Which is what? So this test is mostly about chapter 3 and chapter 4, right? This parameterization business I'm talking about is where? I think it's back in chapter what? Chapter 2. But I just didn't cover it on test 1 because I had pity on you guys. Right? So, but it is something we need to start working on, so I should ask at least a token question on how you parameterize the surface, okay? It's also entirely likely that I give you the parameterization of surface and ask you to do things with it. Like, say, find the normal vector field, right? Or find the equation to the tangent plane. So I hope you're working on the concept of what is a surface versus what is a tangent plane and what the different ways we have different ways we have to look at that, yeah?
Shouldn't you have a 2 in front of the sinh squared theta?
2.
4 times. Oh, sorry. My bad.
Okay.
You're good.
Oh, good. That's relief. I'm not done yet, by the way. Yes, a question? I have made very stupid mistakes today, so anything's possible. Like I assure you, there's no telling what I might do. So the parameterization I would suggest here, if we use theta and beta, would be this. Cos theta, cosh beta, sine theta, cosh beta, 1/2 sinh beta, right? That's my parameterization of the surface. And then if I want to find a parameterization of the tangent plane, well, I guess the question is, what choice of theta and beta gives me 2, 1, 1, right? So if I set this equal to 2, this equal to 1, and this equal to 1, what's theta and beta? Huh? Ooh, I like the last equation. The last equation tells me that sinh beta is equal to 2. So beta is inverse hyperbolic sine of 2, which is a thing. That's a number. You won't find it on your calculator. Which is the log of what? You guys don't remember. No one remembers how to find the hyperbolic sine, inverse hyperbolic sine is the logarithm of an algebraic function? And they teach you anything in Calculus 2? No, if you really remember this from Calculus 2, I would write about it in a letter of recommendation for you. Lost your chance. Lost your chance. But there is a specific algebraic function that you can put here, which then your calculator could do. So there is a way of calculating inverse hyperbolic sine with calculator, But you need to remember what this algebraic function was. I don't remember off the top of my head. I have to work it out. So for our purposes today, let's just leave well enough alone, and there we go. All right. Now what's theta? Ooh, look at this. If we divide x, what's y over x? Yeah, tangent theta, right? And that's also equal to 1/2, right? So theta is equal to inverse tangent of 1/2, which might be a thing. I forget. That might actually be like a not a bad angle. What is it? Can you now there? Yeah, go for it. What's the inverse tangent of a?
It's like
26.7. Yeah, whatever. Okay, so it's nothing nice. So let's just say inverse tangent of 1/2. So then what? Great. That tells me that my point, guys, is that r of inverse tangent of 1/2 sinh inverse of 2 is equal to the 211. People are like, where's the 211? You're like, it's inverse tangent of 1/2 at inverse hyperbolic sine 2. That's the way to get in. It sounded cooler in my head. Anyway. You're like, shut up. We have a test tomorrow. I'm in no mood. Fair enough. Fine. So partial r, partial theta, and partial r, partial beta, these guys are tangent vectors to the coordinate curves on your surface. And so if you plug in the point to those partial derivatives, those give you tangent vectors, and you can use those to build the parameterization of the tangent plane. All right? So like partial r, partial theta is minus sine theta, cos beta, cosine theta, cos beta, 0. Yay. And partial r, partial beta is, by the way, cosine theta, sinh beta, sine theta, sinh beta, 1/2 cos beta. By the way, if you're clever, sometimes you can use, and you notice that we know these things, right? Like this is what? If you look at the point we're interested in, what is this? Yeah. So this is equal to minus 1. How about cos is 2? So this is at 211. All right. And the other one I can actually, can I get around it? Oh, I can't quite do that one. So this one I actually have to think about how to calculate. How about sine sinh? It's not there either, is it? 1/2 cos, But you can figure out values. So like, if sinh beta is 2, then cos beta is what? Well, remember cos squared minus sinh squared is what? So actually cos beta is the square root of 1 plus sinh squared beta, right? So in fact, cos beta equals to 5. Square root of 1 plus 4, square root of 5. So that means that that's 5/2. Okay, fine. I'm going to stop fiddling around here. To be less elegant, cosine theta is what? It is the cosine of the inverse tangent of 1/2, right? Which we could probably improve upon, but I'm just going to go on here. And I still got what? Sinh beta, which was what? 2, right? 2. Wasn't Since beta is 2. Square root of 5. Thank you. Point taken. Square root of 5 over 2. And then what was the, so sine of, so this is going to be 2 times the sine of inverse tangent of 1/2. All right. I'm sorry, I want to talk about something else today, so let me just give these a name. Let's call this one A. Let's call this one B. What's the parameterization of the tangent plane? Let's use, say, S and T. It would be the base point, which is 2, 1, 1. Yeah.
Plus, we'll say S times vector A plus S times, well, T times vector B.
Right. So there you go. That's the parameterization of the tangent plane we're looking for here.
And so if we're asked for the equation of the tangent plane, we simply cross vector A, vector B.
Yeah, if you were looking for the equation of the tangent plane, my advice to you would be go back to how the problem was stated and do what I did at the start that took all of 15 seconds, right?
But you could give us the parameterization and then have this kind of...
That is true. If I gave you a parameterization where it wasn't particularly, I don't know, see, the question is, is there ever an example where it doesn't pay off to just convert it to a Cartesian equation and find the gradient of the thing, pragmatically speaking? I don't know, but you're right. Sometimes if you can't see how to do that, you have no choice but to find the partial derivative, the other partial derivative, take the cross product of those, that gives us the normal, right? So like the normal as a function of theta and beta would be partial r, partial theta, cross product with partial r, partial beta. I'll remind you the picture looks something like this. So we take partial r, partial theta, cross into partial r, partial beta, and that gives us the normal vector field. Right? And then that collection of all linear combinations of these tangent vectors, partial r, partial beta, partial r, partial theta at that point, and gives us the so-called tangent plane, right, to the surface. It all goes back to that picture. All right, enough about that. What was part B?
XY plus 8.
So problem 15, part A, the reason it seems complicated, you guys, is there's 2 things going on. The one thing is finding a parameterization for the given level set, which is a problem in its own right, right? And the second part of the problem is using that parameterization to find tangent vectors to the thing at 2, 1, 1, which, by the way, happens to be a kind of complicated point because you actually have to think about how to choose your theta and beta to get that point. This is something we have not experienced much in our previous examples. Oftentimes when we pick the parameters which meet a certain point, it's been just sort of obvious that we should use 0 or whatever, pi, something simple. This actually required some thinking to figure out what parameters map to the point. So anyway, I'm just trying to say the stars aligned to make that look more complicated than it actually is. Okay. Part B, find the equation of the tangent plane. Now this is a what? This is a graph, right? So, graph, which is a nice case. That means we're looking at z equals to f of xy, right? So the equation of the tangent plane is the graph of the linearization. What's the linearization? Linearization of this function f at the point -1, -2 xy by definition is f of -1, -2 plus the gradient of f at the point -1, -2 dot product with x plus 1, y plus 2. This gives you the best linear approximation to the function at the point. Yep.
Do we say this is a graph just because z is by itself on that side?
Yes.
Or is that one over there also a graph?
Whoop, whoop.
Or a potentially a graph?
No, this would be the graph of, it is the graph of an equation. So if you're interested in talking about graphs of equations, it's, in that sense it's a graph, but when I say graph in here, I'm usually talking about that, which means we can write z as a function of x and y. But you're right that the term graph is used in a more general sense in your previous education. So, I mean, I can't say, oh no, you're wrong or something. I think you're just making a natural extension of the previous use of the term. Because when I teach college algebra, many moons ago, back when you could actually teach college algebra here, right? We did talk about graphs of equations, and that was interesting. Because they have all kinds of really cool things, like they don't have to pass vertical line tests, they can look like all kinds of crazy nonsense. Graphs of equations are exciting. Graphs of functions, so boring. Vertical line test, you know? Ugh. This is that kind of graph. It's a, if you were to, you could use a vertical line test in x, y, z space. You know, if it's a graph of a function, if this is the graph of a function, I pick any vertical line, you know, it's just going to pierce the graph one place. So the graph of a function cannot do anything like cool like this, you know. Like it couldn't, you can't have, the graph like double back and give two different, if f is a function, you can't have that happen. You just have one point on your surface for each choice of x and y as a graph. I'm sorry, I like your question. I want to talk about it more, but it really has very little to do with the test tomorrow, so I should behave. So this f of minus 1 minus 2 is what? Yeah. I sure hope it's 10, otherwise I'm in trouble. Right? Because if this is an element of the graph of f, what's that mean? That's the set of x, comma y, comma f of xy, such that x and y is in the domain of f. That's what we mean by graph in 3 dimensions. So I sure hope that that 10 is related to the minus 1 and minus 2 in the way it's supposed to, is it? Okay, good. That's a relief. 10. What's the gradient here? Yx. All right. And we're supposed to put x equal to minus 1. We're supposed to put y equals to minus 2. I'll do that in the next slot here. So we get 10 plus the dot product of minus 2 comma minus 1 with x plus 1, good grief, comma y plus 2, which is, of course, 10 minus 2 times x plus 1 minus 1 times y plus 2. If you don't like I always think about things in terms of gradients and dot products whenever I can. All right? Some of you don't like that. So if you don't like that, what's another way you could, how else could you understand the equation to the tangent plane? If you want to take all the fun out of it, what is this?
Just unwrap that dot product.
This is z is equal to f of a comma b plus f sub x at a comma b times x minus a plus f sub y at a comma b times y minus b, right? That's what this is. I should say, I'm sorry, I'm still not quite right. Stink. L sub f. Gah. So many letters. So that is the formula for the linearization, right? This is still not the tangent plane. Because so far I've just written an expression. This is a function of x and y. It is the linearization of xy plus 8. The graph of the linearization is the tangent plane. So when I write z, notice I haven't done that yet. Right? Z equals 210 minus 2 times x plus 1, right? Minus 1 times y plus 2 Some of you are screaming in your mind, simplify that already. Fine, if I must. 10, what do I got? Minus 2, that's a 6, right? So 6 minus 2x minus y. There you go. That is the equation of the tangent plane to the graph at that point. In other words, the tangent plane is the graph of the linearization for a function. Any questions? Yeah. Problem 9 on the math battle. Eventually. Oh, yeah, sure. So, guys, for the test tomorrow, what are the big concepts? What are the big ideas? What's that?
Tangent planes.
Yes, tangent plane. I would say that's fair enough. Tangent planes, how to calculate tangent planes either as a graph, as a parameterized set, or as a level set, right? I would say the other big topic is just the geometry of the gradient vector field, right? What's the relation of the gradient vector field to a curve? If we're talking about a function of two variables, right? And how do the contour plots relate to the graph of the function? Remember that? How's that go? What does the gradient of f of xy tell us about f of xy? What does the gradient do? How does that relate to the directional derivative? What's the minimum maximum rate of change, right? And of course, if we talk about the gradient of a function of three variables, then if we set function of three variables equal to a constant, well, that gives us a level surface, right? And the gradient does what? It points perpendicular to the level surface. How do we prove that? That's something you guys should be able to prove. We did it in here. I spent valuable class time going over this. So to prove that the gradient is perpendicular to level surface, we take a curve on the level surface, right? That satisfies the equation level surface, and then we did what? We differentiated that equation. We used the chain rule. We got that the gradient of the level function dotted with the velocity of the curve had to be 0, which said that the velocity of the curve is perpendicular to the gradient vector, right? But the set of all possible velocities fills out the tangent plane to the surface, and that's how we know that the gradient vector gives us a normal to the tangent plane. I spent about 10 minutes to do this. Maybe 5, I don't know. I spent a lot longer than I just said, but we did that in here. So that's something you should be aware of, at least conceptually. And so you notice all of a sudden we bumped into the chain rule, right? To understand that, we have to understand the chain rule. So we got chain rules galore. We got chain rules coming out of our chain rules, coming out of our chain, lots of chain rules to think about. So, of course, before all that, partial differentiation, right? You guys got to know your partial derivatives, which means that you need to know how to differentiate. Now you're in Calculus 3, so odds are pretty good that you know how to differentiate, right? But are there any holes in your defenses? Like if I ask you to differentiate inverse tangent, is that going to stop you? Because it shouldn't, right? So if there's an example I've done in class that you saw me do and you said, oh yeah, I forgot how to do that, that should be a warning to you. I need to know how to do that, right? Not, oh, well, I'll ignore that. It won't hurt me. You won't put that on the test. So what do you guys think I won't put on the test? Tell me. The correct answer at this point is polynomials, right? Sorry, I digress. Now, Nathaniel has asked me about a slightly, well, this is a level 10 monster. I'm probably asking you mostly to battle level 8 monsters on the test, but this is nevertheless a possible test question because we have talked about it. But I view this to be a little bit more sophisticated and difficult. But I have asked it on the test before. Obviously, it's here, right? So we've got two equations in x, y, z, and w, right? And I'm supposed to calculate partial w, partial x holding y fixed, and partial w, partial x holding z fixed. And the question is, what do those look like, right? This isn't yours, it's mine. Did I take this from somebody? Okay. All right. So I guess I just differentiate. So like partial w, partial x holding y fixed should be partial x holding y fixed of this stuff, x plus y plus z, right? Which is going to be 1 plus 0 plus partial z, partial x holding y fixed, right? But what is partial z, partial x holding y fixed? I have also x, y, z equals to 1. So that tells me that differentiating that with respect to x holding y fixed tells me what? It tells me that yz plus x times 0 times z plus x times y times partial z, partial x holding y fixed, is equal to 0. So when I have three things multiplied together, I think of the triple product rule personally, but you can think about it however you like. But the point is that the partial y, partial x is 0 in this case, because we're differentiating with respect to x holding y fixed, right? So partial y, partial x is 0 by assumption. So long story short, we get partial z, partial x holding y fixed is equal to what? Looks like minus yz divided by xy. So I guess I could simplify minus z over x, yeah. So then put that back up in here, we get 1 minus z over x. So yeah.
I was confusing myself by trying the total differential method, and I wasn't entirely sure, how to hold y fixed and so forth. So that's
well, we could do the total differential method also. I mean, that wouldn't be wrong. So that would look something like dw is dx plus dy plus dz. And on the other hand, down here we'd have yz dx plus xz dy plus xy dz equal to 0. My goal would be to solve for, I want to solve for dw, basically. So this dz here, right? Dz is minus yz dx minus xz dy over xy. And therefore, dw, I'm going to have to erase this. Did everybody have this? I thought. I'm going to plug that dz into the top equation, and that'll leave me dw in terms of dx and dy. And then I can read the partial derivatives directly off that.
Okay.
That would be the total differential way to do the calculation.
I guess I just want to see that the top y solving for dz means holding y fixed.
Well, I need to eliminate dz from the top equation to get an equation that just has dw in it.
Okay.
If I'm using z and w as my dependent variables, to understand how w relates to the change in x and y, I need to get rid of that z there. It's clouding the top differential relation. I need to just have dw in terms of dx and dy to capture partial derivatives of w with respect to x and y.
And so that's what's implicit in what you did first by needing to write partial x holding y fixed.
Yeah, yeah.
Okay.
Well, should I finish?
Yes, please.
Yeah. So this will give me dw is equal to, let's see here, 1 minus yz over xy dx plus 1 minus xz over xy dy. And this, of course, would be partial w, partial x holding y fixed. I did some algebra there. What I did was I plugged this into there, and I just rewrote, I collected the things with dx and dy.
So the other one then is partial w, partial y holding x fixed.
Yep. Looks like it's z over y, yeah. Which is probably what I meant to put here, but didn't. I mean, partial w, partial x holding z fixed is yet something else that I haven't calculated yet. Yeah?
So, if you have a problem where you're finding the constant when integrating with respect to partial derivatives?
Sure. Let's see here. How about try to find gradient of f equal to, gee, I don't know, 2y squared, 2x squared, and z e to the z squared. There. That's exciting, I think. So, all right, if I was to do this, apparently I would want to solve partial f, partial x equal to 2y squared. I want to solve partial f, partial y equal to 2x squared. I want to solve partial f, partial z equal to z e to the z squared. So what I would do when I'm faced with a problem like this, a lot of times I'll just integrate each one of those separately. Sort of a partial integration, yeah? And then I look at what I have and I try to see if I can't pick out what's common to build the solution. So let's see here. This, if I integrate with respect to sort of, x, integrate with respect to x, holding y fixed, yeah? That suggests to me that f of xy is equal to what? 2xy squared. Oh, I think I did badly here. I'm missing a very important thing here. Oopsie daisies. That's a 2x, and there's supposed to be a 2y here. Otherwise, it's just not possible. So sorry about that. I should have checked it with the, there we go. So if I have that 2x there, integrating with respect to x, holding y fixed does what? I get x squared, y squared. C is a function of y, but actually also z here. I should really say y and z fixed, right? So that C1 could be a function of y and z. Integrating, hold x and z fixed, right? Integrate. And I should have said f of x, y, z because I'm an idiot. I mean, I'm trying to be less idiotic. So f of x, y, z, integrate with respect to y, right? Holding x and z fixed gives me what? It gives me x squared, y squared, plus, some constant function, quote unquote constant function of x and z. And then integrate with respect to z, right? It suggests f of x, y, z equals what? 1/2 e to the z squared plus c3, which is some function of x and y, yeah? So you tilt your head, squint, what should little f be here then? So we take x squared y squared plus 1/2 e to the z squared, right? And then, plus any constant. That should do it.
Do we not have to solve for the constants so that there looked like there was at least one problem?
There's infinitely many possible f which will do this. Whether or not you have to solve for the constant depends on the context. I've always got time for you guys. Let's see here. Except, no. Well, the question is, do you have time? The question is whether not you guys have time. Number 10. How fast can I? So I would focus on the y component here because it's kind of like it pops out at you. So, I'm not going to copying down the problem I don't have time for, but I can talk about it. Partial f partial y is equal to 3x y squared cosh of x squared plus y cubed, right? So this to me suggests that I should make this equal to my u. So basically, I think about a U-substitution. Integrate, I get f of xy equal to sinh, x sinh, right, of x squared plus y cubed. This partial differentiates to that, right? Do we agree? Differentiate this, we get that. So I'm just integrating the y component with respect to y holding x fixed. Now the cool thing about this is what happens when you calculate the gradient of f. I mean, technically there's plus c1 a function of what? X, right? Forget about that for a second. Suppose you just, maybe we don't even need that. What happens when we differentiate this? We get sinh of x squared plus y cubed, right? Plus what? Plus the product rule, right? So plus 2x squared cosh of x squared plus y cubed, and then 3x y squared cosh of x squared plus y cubed. What is that? That is what was given. So it turns out that we don't need that c1 of x. We could put c1 of x equal to 0, and that f will do.
So what do you mean about solve?
Oh, the solution? Solve? It's literally x sinh of x squared plus y cubed equal to a constant. That's the solution. Because we've proved that the total differential, if we take the total differential of this, right? What's the total differential of c? Right? 0. So if taking the total differential of this gives me sinh of x squared plus y cubed plus 2x squared cosh of x squared plus, me giving you this problem on the math battle is my own punishment because it was begging this discussion, wasn't it? I should learn to put simpler questions on the math battle so I can have easier question days. But the point is, if you take the total differential of that level equation, right? We get exactly that differential equation. So level surfaces of that F are solutions, in fact, to the part B. Yeah.
So when it says solve, we're essentially trying to undo it, turning the
We're trying to
differential-
solve an equation like this, and this is, I would say that this is more of a bonus question for you guys, because I don't think have I asked other homework questions like this?
Yes.
Oh, okay, well then it isn't. I guess you guys should ask me more about that, huh? But to solve an equation involving differentials, what does that mean? If I have, a dx plus b dy equals to 0, what's the solution to this? Basically, you're looking for some function of x and y equal to a constant, right? Such that df is equal to a dx plus b dy. So if you can find a level function which takes that differential equation as its total differential, then that level function set equal to a constant is the solution.
So it's kind of like you giving us the gradient of f and asking the traditional one, just a little different.
Yes, I mean these things are related, but sorry, we should have had a longer talk about this in here. If you're a good student, you realize what this means as it relates to the test, but I won't say any more. Man. Oh well. Good news is you'll come back to this in differential equations. This is the problem of exact equations. That differential equation is an exact equation, and its solution is just the potential function equal to a constant. So anyway, I shut up. See you guys tomorrow.